Now that we have a few models for interactions between particles, it might be important to know what the partition function for those interactions is. We will start by examining the translational partition function because the potential energy depends on the distance between particles, and the distance between particles depends on translations. Remember that when the potential energy is equal to 0, we showed that the partition function for translations was equal to this triple integral. When we include interactions, the total energy is made up of kinetic energy and potential energy. Therefore, the Boltzmann factor in our triple integral becomes E raised to the minus kinetic energy plus potential energy divided by K Boltzmann times T. That can be split up into term Boltzmann factor of the kinetic energy times a Boltzmann factor for the potential energy. We've already included the kinetic energy Boltzmann factor in this triple integral. To include the potential energy, we're going to need to integrate over the positions of all the particles. That information is contained in the volume element in the translational partition function. Furthermore, the potential energy depends on the distance between two particles and not the absolute position of a single particle. Thus, we cannot look at the single particle partition function and must look at the multiple particle partition function. For n particles, the total partition function, often written as a capital Q, is equal to the product of the single particle partition functions, and since they're all the same, that's Q to the nth, divided by n factorial to make sure that we don't overcount pairs of particles. Putting all of this together gives us the following expression for the translational partition function, where we have integrated over the size of the box in each direction for the position of each particle from 1 to n, and from minus infinity to infinity over the velocity particle from 1 to n. Because the velocity is only dependent on the Boltzmann factor for the kinetic energy, and the positions only show up in the potential energy term, we can split this into two integrals and write that the partition function for translation is equal to the product of a partition function for kinetic energy, an integral over velocities, times a partition function for potential energy, an integral over positions. We've already examined the integral over velocities. That's the partition function that we obtained from solving this integral for when the potential energy was equal to 0. We'll be interested now in the potential energy partition function. The integral we need to do for the interactions is the integral over the positions of the particles. That includes the Boltzmann factor for the potential energy. To make this easier, because this potential energy depends on the distance between every pair of molecules, rather than the absolute position of each particle in the system, we're going to express this potential energy as the average potential energy, which we can express in terms of the pairwise potential, and that can be expressed in terms of the position of any two molecules, any pair of molecules. Furthermore, to make this more general, we're going to express the positions in terms of the relative position in the box. So we'll express the x position in terms of its relative position along the total length of the x length of the box, which is a, and the y position as its relative position along the y coordinate, which has a total length of b, and the z position as the relative position along the z direction, which has a total length of c. Making that change of variable and this substitution into our integral, we can write the partition function for the interactions in the following way. Notice that if this triple integral is equal to 1, we're reduced to the case where we have no interactions. This triple integral will equal 1 when the pairwise potential equals 0 because e to the minus 0 is equal to 1, and integrating dmx, dmy, and dmz from 0 to 1 gives us 1. It's often useful to try to break up our model into a term which tells us about the system with no interactions, the ideal case, plus a correction for non-ideality. So we're going to break this integral up into an ideal case plus a term which corrects for u of r not equal to 0. I'm going to split that integral up by essentially adding 1 and subtracting 1 from my equation. Now I have a term that tells me about the ideal interactions where u of r is equal to 0, and a term that contains all the information about the interactions. I can rewrite that by defining I at t as equal to v times this triple integral as v raised to the nth times the quantity 1 plus that integral, which tells me about interactions, divided by v, all raised to the n times n minus 1 over 2. Finally, I will make a transformation to spherical coordinates because my potential, my pairwise potential, is spherical, and I'm going to integrate over all angles because this spherical potential is the same in all directions. That gives me the following form for the integral which tells me about the interactions between particles. When I have a system where interactions between particles are important and I need to model those interactions, this partition function will help me devise a model which takes into account the interactions between particles. We will use this in the next video to find the equation of state for a real gas.